You're right, Paul.
Sorry.
I just see you all.
Okay, well, hello, my name is Alejandro Franco. I came from the National University of Colombia, and I'm a senior student undergraduate in geology. And well, I've been immersed in this problem of attenuation during just 2 months, but this is like well, my preliminary results and how I'd like to contribute to solve this problem. So, well, let's start with the study area. As we had seen previously, we have several nodes deployed in those wind farms, and actually I will be working in the WW station that is within the Pioneer Trail wind farm. And within that area, we have seen many challenges. The first one is that, well, that the station is highly exposed to the noise that is generated by the windmills. And also, we are looking for the traffic that is a rural road that it has almost no traffic. It's very sparse, this rural road, independent on the day. So this is like my motivation to do this work. I haven't arrived to the attenuation part, but this is mainly focused on how can we extract those sparse sorry, those sparse traffic signals, because we need those traffic signals to calculate attenuation. So let's start. There is an existing algorithm that was proposed by Yumin Shao and others, and it extracts those traffic signals. But as you can see, this is 24 hours of data, and we have just 6 in the same day that Alexa showed us in the previous presentation. And also, I needed to tune the parameters of this algorithm in order to refine and make it more sensitive to extract those vehicle signals. But by making it more sensitive to vehicles, I also make it more sensitive to noise. So that's like a problem that that I will show you how I manage it. So this is the time series that is for that day, and we need to convert it through to the frequency domain. I applied a hand window with an overlapping of 50%, and I used 1 second length of this sliding window. So every half second I get a calculation of the fast Fourier transform in order to get a frequency resolution of 1 Hertz. And taking into account that, I got that this spectrogram is focused only on high frequency bands. And in that day, as shown in also Alexa and Cyan, we can see that early in the morning of February 9th, we start seeing like a contamination of noise that is present in the whole frequency bands. It doesn't like have preference for high or low frequencies. And when we try to associate it with like an environmental factor, we can see that it may be caused by wind. Here we can see that this is a very windy day. The maximum wind speed was about 60 kilometers per hour. And I wanted to validate that hypothesis. And the tuning of the workflow that I followed for tuning the parameters was averaging the whole day energy of every timestamp. And by averaging the energy, we got some peaks. This is an example. We get peaks when when we get the more energy by the vibrations, and lower energy when there are, when the noise is quite small. And taking into account like the whole time series, we set up prominence parameter of 0.2 magnitudes, and also a separation between peaks of 6 seconds, because the triangular shape that is characteristic for each vehicle signature only lasts 6 seconds in, it's consistently 6 seconds duration between, in this data. According to that, we can see that the algorithm is very sensitive to noise, and we get, in that day that is actually considered an outlier with high noise, we get like 5,500 peaks, right? And we can see that this is very related with noise. So one of the solutions that we wanted to propose was smoothing the curve. Why? Because we have like a lot of high frequency noise, and by smoothing the curve, we can extract the trend. So we applied a median filter window of 10 seconds, and we start to discard and approve some of those peaks based on the standard deviation from the peaks to the smooth curve. This parameter still needs to be refined, but I'm approaching like the final version of it. So taking into account that proposals, we got these results. As I told you, I still need to refine it, but we get the first the 6 peaks that are noticeable in the time series. Those those are the shapes that how they look like, very consistent. This is also this is how the rejected peaks look like. High signal, a low signal to noise ratio, and even you can see actually if there are vehicle signatures or not. And finally, if we plot the wind speed against the smooth curve, that is that is this same blue curve is that one. We can see that actually both curves fit very well, and taking into account that, I would like to validate that hypothesis preliminarily of the wind speed, wind speed vibrations show us like wind speed vibrations is a good estimation of the background noise and a high or low signal to noise ratio. And also, I'd like to conclude that, those that are my contributions for this problem of the vehicle picking signatures. And finally, the next steps is that I would like to continue with the attenuation problem in this station in order to validate not only in different spaces, but also validate the attenuation variation over different times, and to see if actually it varies it follows the same trends that Alexa and Cyan are seeing for their own results. Finally, this is specifically a purely statistical analysis of it. If you are interested in seeing how can we also see how can we use machine learning to pick some environmental sources of noise, you can attend part has a part presentation of tomorrow that he belongs to the group and he uses machine learning to pick those. So thank you.